we're investigating how to use these really novel tensile, soft, compliant, sort of more biologically inspired robots to explore space. By shortening and changing the lengths of the cables, the whole thing can roll around the planetary surface. Today we're going to be looking at what we call our Super Ball bot, the tensegrity robot that we're designing that is able to both land on a planetary surface, absorbing impact, and is also able then to move around and explore the planet.
This shows the unpacking from a very compact position, to the full robot, which is very important in space travel because your payload fairing volume is a premium. So if you can pack this tightly, you can pack multiple of them, or you can make a very cheap mission out of it. In traditional NASA mission, landing is one of the most difficult, expensive, and one of the most unreliable things about a mission. This is kind of a fundamentally simple landing system. If you can survive a hard landing and you keep that system, you can survive almost anything. You can go off little cliffs, you can go down, steep terrain and so forth. So it really gives you a very secure, robust system.
What you see here in the landing is the central payload, and it's that little sphere in the middle of all the rods. It's protected from impact forces of landing by the elastic absorption of energy in this tensegrity structure. Much like we use our muscles to move our bodies around, we are going to be shortening and lengthening the cables of these structures to create motion by changing the dynamic balance of tensions in the system.
A benefit and a curse of these robots is there's a whole lot of control points and a lot of flexibility. So that's really great in that they can go up hills, they can handle bumps, they can handle uneven terrain, but it's also very difficult to control. So instead of the traditional control kind of top-down, we know how to control something, we just tell it what to do. Instead, our primary approach has been to evolve the control. The best we can hope for is to give it lots of options of what it may do. So we can select hundreds, if not thousands, of different options. Then some are good and some are bad. At the beginning, most of them are bad, but you slowly take the good ones. Like evolution, you replicate the good ones, make small changes, then eventually the good ones get better and better, and out of all the thousands of bad controllers, you actually evolve a few good ones.
One of the interesting questions is, how does a structure like this move through a field of rubble and rocks and whatever you might encounter on the surface of another planet? And so this was an initial first pass at saying, what does it look like for a robot, this type of robot, to encounter a bunch of obstacles and move through them. One of the advantages of a tensegrity robot like we're designing is it's a very compliant and forgiving system. And so we're trying to maximize the ability of the system to move through environments reactively. And then it makes your high-level navigation and control problem a lot easier.
So you can imagine actually putting 4 or 5 all in one aeroshell and all unpacking, very nice and neat. And so you could have a mission where you can have 4 or 5, or possibly if you made them small, dozens or even hundreds, all going at the same time. And then that clip, I believe, showed high-level algorithms of coordination. So you can imagine many of these, that they're all robust in themselves, and then they can all coordinate with each other and perform science quickly and also reliably. If a few of them don't make it, it's okay. The others will coordinate and make up for that.
When you're exploring another planet, what drives the mission is the scientific instruments that you want to bring to that planet to explore, to ask basic questions. We're really looking at this from a fundamental principles perspective. How do you design and control these types of devices? For now, we're building prototypes that are about a meter in diameter, or each rod is a meter long, because that's a nice natural size that you can get lots of components for, motors, and you can fit in your controlled electronics without too much effort. We're currently designing with that target in mind, is that how would you build a system like this that could deliver a 75-kilogram payload to the surface of Titan? But in terms of its potential, you could be building very large versions of these or very small versions. The intuition is that as it scales bigger and bigger, the mass of the system will scale approximately linearly. The same properties hold for a very small version of this, but obviously your payload, your scientific instruments that you're going to bring with you are going to be more limited based on size and mass availability.
Our whole approach has started from the ground up as being a messy system. The integrity itself is messy. The controls are messy. It's oscillatory. The evolution's messy. We're dealing with lots of evolved components. But part of the advantage of that, because at every step of the way, we've had an expectation that things are messy, things are difficult. When we throw little obstacles in its way, it's really not a big deal. We've already encountered so much, which isn't true in a lot of research and a lot of theory, where you have this ideal world, you've assumed perfect vacuums or perfect frictionless environments or perfect precision in everything, and then the world doesn't work. But we've never assumed any of these, mainly because we could never assume any of these. It was from the ground up, very noisy and messy. So that actually gives us an advantage in the future. We can really do all these things, and we can expect it will probably work.